Welcome to the class on process synchronization. Today, we'll explore how the OS manages multiple processes to ensure they operate smoothly without interfering with each other. Let's dive into concepts like critical sections and locks. Process synchronization in an operating system is a fundamental concept that ensures multiple processes can operate concurrently without causing data inconsistency or conflicts. In a multitasking environment, multiple processes may need to access shared resources, such as memory or files. Without proper synchronization, this can lead to errors like conditions, where the outcome depends on the unpredictable order of process execution. The need for synchronization arises from the fact that processes often run concurrently, but may depend on each other's actions. For example, one process might produce data that another process consumes, and if the second process tries to access the data before it's ready, it can have incorrect results. To prevent such issues, synchronization mechanisms like locks, semaphores, and monitors are used. These tools help manage the sequence in which processes execute, ensuring that critical sections of code are accessed by only one process at a time, maintaining data integrity and system stability. Today, we will discuss the bounded buffer problem, a classic example of inter-process communication, IPC, and synchronization in operating systems. This problem occurs when multiple processes, such as producers and consumers, share a fixed size buffer. We have a buffer of size buffer_size equals 10 that holds items and consumed by separate threads. The producer generates items and places them into the buffer. The consumer removes items from the buffer for processing. We must ensure proper synchronization to prevent overwriting or underflow issues. Variables used: we define item buffer_size, stores produced items int and equals 0, points to empty slot. Int out equals 0, points to the next item to consume. Int counter equals 0, tracks the number of items in the buffer. Challenges in synchronization: buffer overflow, if the producer adds when the buffer is full. Buffer underflow, if the consumer removes when the buffer is empty. Race conditions, if both threads access simultaneously. To solve these, we use mutex locks and semaphores to coordinate access safely. Conclusion: the bounded buffer problem is a fundamental concept in concurrent programming. Proper synchronization ensures efficiency and prevents data corruption in multi-threaded systems. We will focus on the producer process in the bounded buffer problem. The producer is responsible for generating data and storing it in a shared buffer, while ensuring synchronization to prevent data loss or corruption. Understanding the producer process. The producer follows a continuous loop, where it performs the following steps: check buffer availability. If the buffer full, counter equals buffer_size, the producer waits. This prevents overwriting existing data. Produce an item. The producer generates a new item, next produced. Insert the item into the buffer. It places next produced at the position indicated by n. The n index is updated circularly, in +1% buffer_size. Update the counter. The counter is incremented to reflect the new item in the buffer. Challenges in the producer process. Race condition: if multiple producers run concurrently, they might modify counter and in simultaneously, leading to incorrect updates. Solution: use mutex locks to ensure exclusive access. Busy waiting: the loop counter equals buffer_size causes unnecessary CPU usage when the buffer is full. Solution: use semaphores to block the producer until space is available. Synchronization with consumer: the producer must not add items when the buffer is full, and the consumer must not remove items when it's empty. Solution: use semaphores, empty, full, to coordinate access. Conclusion: the producer process plays a crucial role in managing shared resources efficiently. Without proper synchronization, issues like data inconsistency, wasted CPU cycles, and process deadlock can arise. By using semaphores and mutex locks, we can ensure a smooth consumer interaction in concurrent systems. Now, we will focus on the consumer process in the bounded buffer problem. The consumer retrieves data from a shared buffer and processes it. Proper synchronization is essential to prevent reading invalid data or accessing an empty buffer. Understanding the consumer process. The consumer follows a continuous loop and performs the following steps: check buffer availability. If the buffer is empty, counter equals 0. The consumer waits. This prevents accessing invalid or non-existent data. Retrieve an item from the buffer. The consumer takes the next available item, next consumed. Update the buffer index. the out index is updated circularly. Out +1% buffer underscore size ensures that it correctly cycles through buffer slots. Update the counter. The counter is decremented to reflect that an item has been removed. Challenges in the consumer process. Race condition. If multiple consumers access the buffer simultaneously, they might modify counter and out incorrectly. Solution. Use mutex locks to prevent simultaneous access. Busy waiting. The loop while counter == 0 causes excessive CPU usage when the buffer is empty. Solution. Use semaphores to put the consumer in a waiting state until an item is available. Synchronization with producer. The consumer must not remove items when the buffer is empty, and the producer must not add items when it's full. Solution. Use semaphores, empty, full, to coordinate access between producer and consumer. The consumer process is responsible for retrieving and processing items in a multi-threaded system. Proper synchronization mechanisms, such as semaphores and mutex locks, ensure smooth operation and prevent issues like data corruption, conditions, and wasted CPU cycles. By implementing these synchronization techniques, we can create efficient and reliable inter-process communication. The bounded buffer problem is a classic example of inter-process synchronization, where multiple processes, producers and consumers, share a fixed-size buffer. Proper coordination is essential to avoid race conditions and ensure data integrity. Atomic operations in bounded buffer. The statements, counter ++, incrementing the buffer counter, decrementing the buffer count, must be performed atomically to prevent incorrect updates when multiple processes access counter simultaneously. What is an atomic operation? An atomic operation executes completely or not at all, without interruption. If these operations are not atomic, race conditions may occur, leading to inconsistencies of counter. Ensuring atomicity. To guarantee atomic execution, we use synchronization mechanisms such as mutex locks, prevents simultaneous access to counter. Semaphores, controls producer and consumer access. Conclusion. Atomic operations are critical in concurrent programming. Using synchronization techniques, we ensure efficient and deadlock-free bounded buffer system. The bounded buffer problem involves a shared buffer, where producers add items and consumers remove them. A critical aspect of this problem is ensuring the correct update of the shared variable counter, which tracks the number of items in the buffer. Non-atomic execution of counter ++ and counter. The statement counter ++ may be implemented in machine language as register 1 equals counter, load counter into a register. Register 1 equals register 1 + 1, increment the value, counter equals register 1, store back to counter. Similarly, counter may be executed as register 2 equals counter register 2 equals register 2, 1 counters register 2. Since multiple processes may execute these instructions concurrently, a race condition may occur, leading to incorrect values. Ensuring atomicity. To prevent race conditions, we use synchronization mechanisms like mutex locks, ensures only one process updates counter at a time. Semaphores, control access to shared resources. Conclusion. Without atomic operations, concurrent processes may lead to data inconsistencies. Using proper synchronization ensures the correct and safe execution of the bounded buffer problem. The bounded buffer problem involves a shared buffer, where a producer adds items and a consumer removes them. If both processes try to update the buffer simultaneously, their instructions may get interleaved, leading to race conditions. Interleaving and scheduling. Since assembly instructions execute in multiple steps, concurrent execution may cause loss states. One process overwrites and others change. Inconsistent buffer state due to improper sequencing. The extent of interleaving depends on process scheduling by the CPU. Solution. Synchronization. Using mutex locks or semaphores, we ensure that only one process updates the buffer at a time, preventing race conditions. Conclusion. Proper synchronization prevents errors caused by interleaved execution, ensuring safe concurrent access in the bounded buffer problem. The bounded buffer problem involves shared memory access between a producer and a consumer. If both processes update the counter variable concurrently without synchronization, it can lead to race conditions, where the final value is unpredictable. Example of an interleaving issue. Assume counter equals 5. If the following sequence occurs, producer, reg 1 equals counter, register 1 equals 5. Producer, register 1 equals register 1 + 1, register 1 equals 6. Consumer, register 2, equals counter, register 2, equals 5. Consumer, register 2, equals register 2, 1, register 2 equals 4. Producer, counter equals register 1, counter equals 6. Consumer, counter equals register 2, counter equals 4. Now, counter equals 4 or 6 instead of 5, causing data inconsistency. Cause of the problem. This happens because counter is updated in non-atomic steps, an incorrect interleaving of operations. Solution: synchronization. The bounded buffer problem requires proper synchronization to ensure that the producer and consumer processes access the shared buffer safely. A simple approach is to use two processes, P, producer, and P, consumer, with a structured execution pattern. Process structure. Each process follows a repeating cycle. Entry section. It's safe to enter the critical section. Critical section performs operations on the shared buffer. Exit section updates shared variables and allows the other process to proceed. Reminder section executes unrelated tasks before re-entering the loop. Synchronization challenge. Since both processes share common variables, improper link can cause race conditions. Simultaneous updates lead to incorrect values. Deadlocks. Both processes wait indefinitely. Starvation. One process never gets access. Solution: synchronization mechanisms. To prevent conflicts, we use